So let's look a little bit more at resistors, capacitors, and inductors. So resistors are ohms. This is the top left one. We've looked at these a bit. So below I have a couple pictures of resistors. And there's a couple different ways to read the resistor values based on their colors and the lines of their colors. And we'll look at that a little bit more in the future. But I just want to get you to know that there's a whole bunch of different types of resistors based on what material they're made from, based upon their manufacturing process. In the bottom left, we see different wattages allowed for resistors. So let's just say a resistor is rated for 1/4 watt carbon resistor. And that's a lot of ours are like 1/4 watt carbon, 1/4 watt metal. Usually in the lab, you'll see mostly a fourth a watt. So that's kind of like their power rating. If you go significantly beyond that, you can essentially burn out your resistor very quickly and leave a black little smoky mess behind. So different types of materials are going to allow you to do different wattages, and there's a couple other things that are going on behind the scenes there too, but I just want you to know that resistors, you want to size the correct wattage for what you're doing in electrical, otherwise you can have problems there. So resistors are pretty much the most self-explanatory. The next ones we have here are capacitors, and that's a symbol for capacitor. And capacitors come in a whole bunch of different types: electrolytic, tantalum, many types. And I have a slide coming up on that too that you can kind of look at it. And then finally on the right hand side we have inductors, which is given the term L, and they're measured in henries, and you get a symbol like that for an inductor. An inductor really is kind of a simple thing. It's just a piece of magnetic wire that is wrapped around some kind of coil, usually a ferrite-based coil. And inductors have some fantastic uses in electrical engineering too. But between these three different elements, these are the primary tools of electrical engineering. And we're going to go through those in a moment. So here we have the same circuit components I was talking about: resistors, inductors, and capacitors. I'm going to go through a little bit more of the basic theory behind them. So a resistor, the symbol for that is R, and we measure it in the units of ohms. And that's the symbol for the resistor again. It's like a zigzag line. So a resistor's primary function is it takes energy and it turns it into heat. And by doing that, it can remove some of the energy from the system. So a very common place to see a resistor that we'll do in lab is putting a resistor and sizing the correct size of resistor, the correct ohmage of resistor, correct resistance of resistor, in order to protect an LED so that we can not burn the LED out. Because most LEDs, if you let 9 volts go through from a 9-volt battery, your LED is going to go really bright for about 2 seconds and then burn out immediately. And that's undesirable because you want an LED that lasts a long time, not one that glows brightly for 2 seconds and is done. So a resistor is a way from taking some of that extra power that's generated there from the 9-volt battery out of the system to essentially protect the LED and let that the correct amount of power through the LED for optimal lighting. Another good example of a resistor is an incandescent light bulb, and you can see a picture of one there next to the resistor. And an incandescent light bulb is actually a very great example of resistors. So what you have there is you have house current, which is alternating current, going through that bulb back and forth. And the light bulb functions, the filament there functions as a resistor. And as the current goes back and forth through that resistor gets hotter and hotter and hotter. And it's actually the heat, eventually it gets to a certain point of heating, that it produces light. And that's some of the physics that we've had in Physics 2 and E&M. But it's a very good example, though, of essentially how a resistor works. You're taking a lot of extra energy into the light bulb, and you're heating a filament up with it, and that energy is being removed as both heat and light coming out. Primarily heat, though. So the next one over we have is the inductor, which the symbol we have for that is L. Why not I? Well, I we already used for current, so we needed something else, so we use L. And the unit of that is in the Henry, or henries. And inductors are pretty cool. They store energy in a magnetic field created by current flowing through a coil. So essentially, when you plug, let's just say we have a resistor and a battery. When we plug that resistor into the battery circuit, power essentially immediately goes through the resistor, and the resistor starts heating. For an inductor, however, as soon as we plug that inductor in, the current doesn't immediately go through. It slowly builds up because it's essentially the inductor, the way I think of it, the inductor converts some of that current into a magnetic field, and then it stores that magnetic field. Because creating a magnetic field like that isn't immediate. That happens over time. It could be up to a second, even longer if you have a really big inductor. And we can look at the equations for that later. But essentially, you're storing some of that energy from the current in this magnetic field. And then let's just say you unplug the inductor from the circuit. Immediately when you unplug the inductor from the circuit, that magnetic field doesn't immediately go away. It's still there. It's still present. So that magnetic field slowly goes away and actually generates a small amount of current with it as well. So essentially, you can think of inductors as resisting changes in current. If you quickly plug an inductor into a circuit, it's going to pull some of that current out of it and turn it into a magnetic field. And if you unplug that inductor from the circuit, immediately it's going to turn some of that magnetic field back into the current, back into some small current. So it resists changes in current. I have a good slide coming up too that we're going to look at that as well if you want to learn a little bit more. We're going to do a lot more with inductors later on in class when we get to RCL circuits. Finally, we have capacitors here. And capacitor, the unit for that is C, and that's the abbreviation is C, the unit is farads. And the symbol of capacitor there is two plates, essentially, because remember, we're having charge build up on one of the plates. So what capacitors do, they store energy through charge. So an electric field in the plates. So if you look up on the picture that we have right here, we have positives all on one side, we have negatives on the other, and there's some kind of insulator between the two. And that essentially insulator has an induced charge on it. So if there's a lot of positives on that orange one on the left, that's going to make a lot of negatives on the insulated piece in the middle get attracted towards that side of it. And the negatives there are going to push the positives to the other side towards the blue, and that's going to induce a negative on the blue side. So essentially what capacitors do is they resist the buildup of charge. So in some ways it's similar to an inductor in the reverse, though. Inductors resist changes in current. Capacitors resist buildup of charge, resist that. So we're going to go into some of the mathematics behind that. You should have had some of this already in physics, but we're going to go a bit more in depth into this course. So another important piece of electrical technology or component that we have is called the diode. And diode's technical term for them, it's an electrical device allowing current to move through one direction with far greater ease than the other. The way I like to think of a diode is that it is a one-way resistor. So not the complete technical definition, there's a lot more going on there, but as an easy definition, so diode only allows current to flow in one direction, and when it does, there's a resistance of that diode. However, if you plug the diode in backwards compared to the power supply, essentially current isn't going to be able to flow to whatever device is coming after that. So it acts then as a brake in the system. Diodes get a little more specific than that due to forward biasing diode and reverse biasing diode, and you get also some interesting properties if you're going close to the rated voltages on them. However, for a very simple introductory part of diodes, you can think of them as a resistor where current flows only in one direction. It flows in the direction of the electron movement. So at the bottom there, we have a couple diodes out. These are all through-hole diodes, and we know they're through-hole, and we'll talk about that a little bit more in a minute. But they have essentially these long metal pins that come out of the sides, and those go through holes in the circuit board to be able to be soldered down and attached. That's why we call them through-hole. So diodes, essentially, you can see how they look. They look a little similar to resistors sometimes, but they have a different classification. Often diodes you'll find as black with a little white band around it on the side, and that indicates the direction of the diode, so you have directionality. And that's common usually on all diodes, that one of the sides of the diodes will be capped. That way you know if you're plugging it in so that current can flow through it in the right direction, or if you want to plug it in so current can't flow through it in that direction. So transistors, PNP or NPN. Essentially, these are both bipolar junction transistors, BJTs, you'll see. And essentially, if you remember from the slide previous to that, how we looked at PN junctions and NP junctions, a PNP junction is essentially kind of a stacked set of diodes that are built in. So they always have, transistors always have three legs that come off of them. One of them's the base, one of them's the collector, and one of them's the emitter. And essentially what they do is they allow for an amplification of current going through them. Essentially, you can use them to do some very basic audio amplification. Even more general use for them is actually using them as electronic push buttons, which is an interesting way too. So if we look at the top left, we have an NPN transistor. And what that's saying is that there's some kind of load on the voltage positive side going to the collector. And if we add some kind of voltage to the middle pin at the base, the power is allowed to flow from the collector to the emitter. It flows through there, and that's why we have that red little IC going down. If there's no current going into the VB, then you're not going to have current flowing from the C to the E, from the collector to the emitter. Now, in a PNP transistor, on the other hand, the positive voltage is given to the emitter terminal, and the current flows from the emitter to the collector. So it's kind of almost, it's kind of flipped around a little bit. And that means if the base isn't grounded, then essentially current isn't going to flow through the transistor. So if you have a break there, or there's some kind of applied voltage, or something's happening there, essentially you can't have electricity to flow. So you can see how we might use these as push buttons, actually. So if I have this whole system set up from that, essentially the load, collector, emitter, until there's a voltage applied on the base, it's a gap in the circuit. So let's just say we apply a little bit of electricity from something else. Now power can flow through it, and now we have essentially a closed switch. So power is flowing through. So underneath at the bottom, you can see a couple different packages for transistors. Bottom left is the one that we'll use most likely in class. The one next to that, you'll see that there's essentially a slightly bigger package to it. The pins are a little bit thicker, and on the back you'll see a giant piece of aluminum, and that piece of aluminum is actually a heat sink, because transistors can get pretty hot, actually, especially if we're getting into bigger, higher power ones like MOSFETs or whatnot. You need some way to cool them down, and so that big aluminum kind of blocky part on the back helps. However, sometimes even we will put that and attach that to a much bigger heat sink, and that way we can really dump heat. So we do that a lot in satellites, actually, because there's no air up in space, so we need some way to be able to dump heat out of that transistor. And the only way to do that is with a surface contact, a big surface contact. And the bigger the surface contact, the more heat flow, which we have in basic thermo. And so that tab in the back allows also for a larger surface area for heat to flow out of the transistor, keeping it cool, because these overheat relatively easily if they're not properly taken care of. On the bottom right, we have a couple other packaging ways of packaging PNP and NPN transistors. The biggest way I kind of understand if it's a PNP just by first look is, does it have 3 pins? And if it has 3 pins, then then I kind of look into, okay, let me look up what kind of transistor this is, based on usually the numbering. So you can't really see it on these. Usually they'll say PNP or NPN, or sometimes they'll just give a part number, and you'll have to go on to Google and find the datasheet for that somewhere. So like I was just talking a slide or two ago about the different packaging of electronics, so this is another type of electronics packaging. This is where essentially you package the individual, essentially the individual chips themselves. And so you can see here just a few different types of packaging. Some of the most used that we're going to use in class that you're going to see are DIP or DIPs, dual inline packaging. We have PDIPs, we'll see those a bit, TO, 220s. Essentially, this is there's many more than this, but this is a nice little selection of the most commonly seen ones. So some of these are through-hole mounts, and those through-hole ones have little legs that go down through the circuit board, as opposed to surface mount ones, which the legs stick on the top of the surface board. So the way I kind of like to remember that is, if the legs feel kind of pokey, and they're going to poke down into something, then that means, to me, that's going to be usually a through hole. And if the bottom of the legs feel kind of flat, then that's usually going to be a surface mount. So here we have a slide showing the through hole versus surface mount of different things. And I pulled this off of actually CTE, coefficient of thermal expansion slide. So one of the big things that mechanical engineers will do for circuit boards is to calculate the solder fatigue and solder joint fatigue. So when does the solder crack? Because remember, these chips are going to get hot and then they're going to get cold, and they're going to go through a lot of thermal cycles. And even the thermal cycles when they get soldered, so like wave soldering has usually goes through, and essentially wave soldering, you heat the entire circuit up and you run some solder over top of it. But wave soldering lets a lot of the components get hot too. And sometimes for wave soldering, you can go through 10, 15, 20, even more thermal cycles, depending on the types of parts that you have on the board. So one of the big things for mechanical engineers is to look at how the solder fatigue analysis of those circuits are. But the point I wanted to make with this one is on the top left, we have a surface mount component. You can see where the solder joint is, and that solder joint essentially connects the component to the board. And the component there, like I said before, it's flat. It doesn't have anything really, like the legs of it aren't pokey or whatnot. This piece is just a flat package. It's like a little tiny rectangle that gets soldered down to the board. If we look directly underneath of that, so this is another type of package where they have legs, but the legs are flattened at the bottom of them. And that allows for a really nice solder joint contact there. So you get some solder in between the two of those, and that makes sure that you have enough surface area with contact to the solder joint that you get a nice mechanical connection there. And the leads, or the legs of the circuit in that regard, are usually actually bent with a tool to make sure that they have very, very specific angles of bending, because that's going to relieve some of the stresses on that component. The worst thing that you could have is something going through a lot of thermal cycles, expanding, contracting, and then a lead breaks off, or a leg of that breaks off, and then that would lead that entire circuit potentially to disarray. So that's something we want to look at too. On the very right-hand side, you see a through-hole one. So you can see this long leg, this long lead going the entire way through the circuit board, and solder is just being essentially pumped the whole way in between those. And so this could be going through a via of some kind in the circuit board, or some other designation that we have designed into the circuit board to hold it. But through holes have a very, very high amount of contact and mechanical contact between the lead and the circuit board itself, and that can be desirable if you're going into something with that requires more stress. However, with that being said, since there's a longer leg there can also be more vibrations building up. So more vibrations in some cases can actually make this a weaker connection as well. So that's something we want to look at as well. But I just wanted to introduce some of the different packaging types through this slide.